We will now move on to solar power. We will talk about concentrated solar power and photovoltaics. In general, solar power has many features similar to wind power. It is a renewable energy source, which means it does not produce lots of greenhouse gases during operation. As it is dependent on the sun, its production will be variable. This means we will have seasonal, daily and hourly variations of our output. Again, similar to wind, it has low operation and maintenance costs, but again, quite high investment costs. However, it should be noted here that these costs are decreasing rapidly in the last years. The energy output is therefore also very site-specific. For osmosis, we will talk about two types of solar energy: concentrated solar power and photovoltaics. For concentrated solar power, various forms of collectors can be used to channel solar radiation onto a receiver. This heat can then be used in a steam turbine in large power plants. But there are also investigations going on for smaller power plants, which would use microturbines or Stirling engines. CSP plants imply high capital costs, not only due to the component costs, but also due to engineering. These costs can be mitigated over time due to low operation and maintenance costs. Utilization is very site-specific. Commercial and scientific power plants exist, amongst others, already in North America, North Africa and Saudi Arabia. Concentrated solar power is a developing technology. It is right now not competitive with PV panels. However, there is high potential in combination with thermal storage solutions. PV panels are usually silicon-based crystals utilizing the photovoltaic effect of light photons to generate an electric current. Efficiencies of PV panels can surpass more than 40%, but an average efficiency in most commercial cases is assumed to be around 15%. This value is rarely reached per year in northern regions. PV panels can be considered a very mature technology, and there are many products available on the market. However, this is also still an uprising technology, and there are many different technologies being developed right now for the market. This effort in research and development has also led to a rapid price decrease for PV panels in the last decades. As mentioned before, solar energy is a very fluctuating energy resource. Therefore, it is often combined with some sort of energy storage. For concentrated solar power, this may be some sort of heat storage. For photovoltaics, this may be some sort of electrical or electrochemical storage, for example, batteries. How we model the storage for our solar energy depends on the design of the facility. In osmosis, there are two possible ways to model storage. Firstly, we can adjust our production curves of our solar power plant. This is usually good enough for long-term modeling. Secondly, we can add our storage as an additional element in our model, similar to hydro storage. Similar as with wind, if the exact same group of solar power units is installed in different locations, the parameter that changes is the capacity factor. In countries with good solar resources, photovoltaics have already reached the so-called grid parity. This means that the levelized costs of electricity are equal or lower than that of conventional energy sources. The most distributed commercial PV technologies are wafer-based crystalline silicon and thin film. As mentioned before, CSP is not yet cost competitive. However, the potential is increasing constantly. On the right, we can see again some key characteristics for large-scale utility PV plants and for CSP plants. As we can see, for example, the capital costs of large-scale PV power plants range from $1,700 to $2,100 per kilowatt. In comparison, those of CSP plants are much higher, ranging from $4,500 to $8,000 per kilowatt. For residential PV, again, if the exact same group of solar power units is installed in different locations, the parameter that changes is the capacity factor. Compared to large-scale PV power plants, residential PV has, in general, higher capital costs due to economies of scale. Practically, this would mean, for example, that we have capital costs of $2,200 to $4,500 per kilowatt. Just as with wind, for photovoltaics or CSP, no input technology is necessary, as we do not model the sun. However, generation and available power can be calibrated by using capacity factor and availability factor. There are several ways to estimate the capacity factor. Here we will propose one way. We can use historical data of wind or solar generation
for 1 year or several years, and then divide this value by the installed capacity times the amount of hours in 1 year. This will give us the historical average capacity factor. We can then look for hourly data on the internet. One such website could be Renewables.ninja. Here we can download hourly data on solar and wind in a certain region. We can then extract the average capacity factor for each time slice. Adjusted capacity factor for each time slice is equal to the average capacity factor of each time slice, as we got the data from Renewable Ninja, times the average capacity factor of our historical data, divided by the yearly average capacity factor from Renewable Ninja. Again, Renewable Ninja is just an example for one website. You can use any data from any website. There are several key parameters which we have to consider when defining solar and wind power plants in OSeMOSYS. First, the output activity ratio. This defines the rate of fuel provided. Second, the capital costs. We normally use millions per gigawatt or dollars per kilowatt. This defines the overnight investment costs into the power plant. Thirdly, the fixed costs. Again, here we use normally millions per gigawatt or dollars per kilowatt. This defines the fixed operation and maintenance costs. The variable costs, again, normally in millions per gigawatt hour or dollars per kilowatt hour. This defines the variable costs of the power plant. The availability factor. This is a factor which accounts for planned outages. The factor ranges from 0 to 1 and is used for the entire year. The capacity factor. This represents the variability in generation of the power plant at each point in time, depending on the availability of resources. This is probably the most important factor for our wind and solar power plants. The operational life. This defines the lifetime of the technology. There are also some optional parameters which we can use for our model in OSeMOSYS. Those are the residual capacity. Normally we use gigawatts. This defines the existing total capacity available in each year for a specific type of power plant. We can also use total annual maximum capacity and total annual minimum capacity, again in gigawatts. This defines the total maximum or minimum existing capacity allowed for technology in a specific year. The total annual maximum capacity investment and the total annual minimum capacity investment. This defines the maximum or minimum planned new capacity allowed to be installed for technology in a specific year, again in gigawatts. Thank you for your attention.